Uh, it's a great pleasure today to have Bishal Deb, an old friend of ours from University College London, and he's going to talk about analyzing a strategy for oops, a strategy, analyzing a strategy for a card guessing game via continuously increasing subsequences in multiset permutations. Bishal.
Okay, let me share my screen. All right. Um, are my slides visible?
Yes.
Okay. So hello everyone, and I would begin by thanking the organizers for giving me this opportunity to talk at this seminar. It's wonderful to be there at IMSC virtually, but I would like to be there at IMSC soon in person. Hopefully, it's been a while since I've visited Chennai. Um, so, uh, so I'm going to talk about this work, which is based on. So this is based on joint work with my co-authors Alexander Clifton, Yifeng Huang, Sam Spiro, and Semin Yu. And we started working. So the story is we met at this conference, Graduate Students Combinatorics Conference. So this was a PhD students conference organized by PhD students for PhD students sometime in April. And there was this open problem session, and so Sam posed this problem, and then we started discussing about it, and we ended up solving it. And so this work is based on this. So it's been a wonderful journey, and I mean, all of us have very different backgrounds and very different areas of comfort, and mm, I, and all of us have learned quite a lot. And I don't think any of us could have been able to solve it uh, without having help from the others. And in fact, we've learned more than uh, I mean, yeah, we've learned, all of us have learned something new from this. So this has been wonderful. So let me begin. So imagine you have a deck of, so you have a deck of cards. You have got mn cards, and the cards are labeled 1 through n. And there are m different suits. So they have been shuffled uniformly at random. And then what I do is I pick the topmost card and I ask you to guess what it is. So I'm not asking you to guess the suit. I'm asking you to guess the label, so the type. So in the case of the usual deck of cards, where we have where m is equal to 4, n is equal to 13. Let's say the topmost card is Queen of Hearts. Then I'm asking you to guess Queen, not Hearts. Uh, so I ask you to guess the topmost, guess the card, and then I reveal partial information to you. So I tell you whether your guess is correct or wrong. I don't tell you the card after you've made the guess. So I do not reveal the card to you. And then I discard the card. I do not put it back into the deck. And then we move over to the next card. I ask you to make a guess again. And so you would want to maximize the number of correct guesses. So let's look at a few strategies. So one strategy is you keep guessing 1 at each turn. So then you are guaranteed a score of, so this is a deterministic strategy, and no matter how the cards are shuffled, you're guaranteed a score of m, because 1 occurs m times. So this is the trivial strategy. Can we do better? And let's look at another strategy, which is the safe so it's called the safe strategy. So keep guessing 1 until all ones are correctly guessed. Once you have guessed m, like once you have gotten a score of m, then you start guessing 2 till all the 2s are correctly guessed, and so on. So in this strategy, now you are only guaranteed a score of m. And if you are extremely lucky, you may get like a maximum possible score of mn, or else so worst case, you'll have a score of M. Best case, you'll have a score of Mn. And Diaconis, Graham, and Spiro showed that the expected score is M plus 1 minus 1 over M plus 1 plus an error term. So here, now we are talking about expected score over all possible random shufflings of the deck. Instead of, you are not guaranteed a score. All right.
When you say this, for this strategy, you mean?
Yes.
For this particular strategy of.
Yes. So in this strategy, so in the previous strategy, you are guaranteed, no matter how the cards are shuffled, you're guaranteed a score of M. So your expected score is equal to the deterministic score that you have, like M.
Yeah.
But here your expected score is M plus 1 minus something plus an error term.
I'm a bit confused. How is this thing is less than 1?
Sorry?
Shouldn't the expected score here be greater? Do you mean M plus this or?
Here, yeah, I mean M plus 1 minus 1 over M plus 1. So this is still greater than M.
Okay.
It's still
I put
greater
those
than M.
in parentheses. Yeah. Okay, fine.
Yeah. By the way, is my cursor visible?
Yes.
Okay. Now, the next strategy is the shifting strategy. So in this strategy, what you do is you keep guessing 1 till you encounter a 1 once. And then you keep guessing 2. And then 3 and so on. So in the previous strategy, you kept guessing 1 till you guessed all the ones. Here, what I'm asking you to do is guess a 1 till you hit it at least exactly once. Then you keep guessing 2 and so on. If you are extremely lucky, you've guessed all the numbers from 1 through n. Then make an arbitrary guess, or you can, but we are not really concerned with that in our problem. And this is the strategy that we analyze. So let's restate this in terms of counting longest increasing subsequences. So for that, I'll have to introduce this object called, which we call a multiset permutation. So begin with.
No, I didn't quite understand the strategy. So make arbitrary guess after all numbers are guessed at least once.
Yeah.
So you after, so let's say we have guessed all the numbers correctly, then you just choose at random and do it.
Yeah, I mean, we aren't really concerned with that part of. So okay. What I want to say is here, if you're extremely so the best, I mean, if you're very unlucky, the best score that you could get is 1, because you'll keep guessing 1. But imagine it happens that all the M1s are at the end of your deck. So you're guaranteed a score of 1. And then in the best possible scenario, you guess everything from 1 through n, and then you get a score of n. But then that is very unlikely. And if you have guessed everything from 1 through n at least once, after that, what happens? We are not really concerned. So what I want to say is then you're guaranteed at least a score of n. So we are really, I mean, your score would be a so what the quantity that we are trying to compute is going to be a lower bound of the score. Like I'm going to say that at least I'm guaranteed a score of this. So I'm not really concerned about what happens. Like, let's say we stop guessing.
Okay, got it. Okay.
Yeah. I mean, you can certainly do, sorry, yeah.
No, go ahead.
So we can certainly do better, but this is what we analyze, at least.
Yeah, actually, I was going to ask you about the certainly do better business. So of course, there's an optimal strategy where with whatever information that you have at any given point, you can infer a probability distribution on the
yes
thing, and then you just guess whichever one of the things which has highest probability, right?
Right. So maybe I'll talk about the other known strategies and like give an overview of that at the end. I'm guessing I'll finish very early, but yeah, I'll probably mention a bit about that.
Okay.
Yeah.
So what is the motivation for choosing this particular strategy? Was this an open question or something that was in
so
that paper of diagonal?
this was, yeah, this was, so I'll get to it. I'll get to it in a while.
Okay.
So take M and N. Natural numbers, positive natural numbers, I insist. And now a multiset permutation, it's a word pi, where your alphabet is, it's a word pi, which is of length mn. Your alphabet is 1 through n, and each letter is repeated exactly m times. And let Smn denote the set of multiset permutations. So let's look at an example. So here pi is equal to this word. So you have the letters 1 through 5, each occurring twice. So n is equal to 5, and m, that is the number of, that is the multiplicity of each letter, that's 2. Okay. Now what we are, so we want, so the quantity that we are interested in, so we want to compute the maximum j such that 1, 2, 3, and so on till j is a subsequence of pi, not a subword. That is, they may not occur consecutively within pi. So we want to compute what is the max j, and that is the score that we will get if we apply the shifting strategy, which is, so that is to say, if you keep guessing 1 till you hit a 1, so that's your first occurrence of 1. Then you keep guessing 2, and then, so if j is the maximum such subsequence, and you have guessed 1, 2, 3, and so on till j, then you're guaranteed a score of j. Sorry, then your score will be j in that shuffle. So in for so pi denotes. So I forgot to mention this, but let's say you've shuffled a deck of cards, then this multiset permutation pi denotes the sequence in which the cards will appear. So pi here is your deck of cards. I mean, yeah. So it's chosen uniformly at random from SMN, and let's call this quantity as L1 Mn of pi. So let's look at the same example again, and if you look at the numbers in red, then you see that L125 of pi is equal to 3, because you have the sequence 1, 2, 3 over here. So 3 is the maximum j. And so if your cards were, so if your deck was given by this pi, then you would have a score of 3. So of course, there is no reason to start from 1. You could start from some I, and then you could ask, what is the maximum j such that I plus 1, and so on till j is a subsequence of pi. And so in the same example, if you start from 2, then your score is going to be 4. But of course, like when you're playing the game, you do not know which I is going to maximize this. So we are not going, but this is a question which is of interest, which is, what is the, so we call these longest continuously increasing subsequence. So you can ask, what is the longest continuously increasing subsequence? So that is a question of interest. But yeah, in a priori, we do not know which I is going to maximize this. So so in this talk, we are going to compute the expectation of this quantity. So when pi is chosen uniformly at random, this is a random variable, L1 Mn of pi. All right. So any questions?
Are you going to also look at the joint distribution of LIMN?
No, we haven't done that actually.
Is
That's
it
a
different? I mean, it seems to me like it might be the same, right? L2 or N up to.
so I mean, if you all right. So if I is, this is what I intuitively think will happen. If I is fixed and a small fixed natural number, then if you pick M and N large enough, it won't matter much.
Right.
But then let's say I is chosen something very close to N. then of course it's going to be very different.
What I mean is that for small values of LIMN, the probability should be the same.
Yeah, so small values of I, the expectation of
No, given I for small values of the
MNN.
statistic, no.
Oh,
So
okay.
the small values of the random variable, the probability should be.
Yes.
And it's just a truncation of I mean, and then.
Okay, so but wait a second before you go further. This I plus 1 through j is not cyclic. You're not going beyond. You're not wrapping around.
No.
Of course. Okay.
But at least
Only then
till you reach n, there should be no difference, right? Whether you start guessing with 1 or you start guessing with 2.
Yeah, so that's what I was a little confused. So it shouldn't matter which I choose if I'm going cyclically, but I guess you're not going cyclically, so the question makes sense.
Yeah, but the only difference is that you'll end somewhere at n, and after that, but until then, your probabilities should be the same. And,
also another question, Bishal, is suppose I have 1, 2, 3 n, 1, 2, 3 n, 1, 2, 3 dot up to n, 1, 2, 3 dot up to n, 1, 2, 3 dot up to n. What is LMN1 then?
That's n.
I see. After that, after you, and then after that.
Okay. So the point is, you're guaranteed at least a score of L1 Mn of n of pi. So you're guaranteed at least that much. So, I mean, if you think in terms of the score that you'll obtain, you are guaranteed at least a score of this quantity.
Okay.
So we are primarily interested in this quantity.
Hey, I just have a question. You may have explained this, so sorry. You have here max j such that I plus 1 up to j is a subsequence. And then in red, you have 2, 3, 4, 5. So shouldn't j be 5?
Yes. Thank you for pointing that out. Okay, so I define. So here I define LIMN of pi to be equal to j minus I plus 1.
Okay, so it's the length. L is
is the length. Is the length. Right. Okay. Thanks for pointing that out. But yeah, I mean, I haven't written it, but I guess I said that. Right. Thanks for pointing that out.
I guess your title gives it away, right? Longest continuously increasing.
Yeah.
So
all right. Yeah.
For m equal to 1, what is the answer? That is, if it's a pure permutation.
That would be m equal to 1.
So for m equal to 1, you mean what is the expectation?
Yes.
Right. So the expectation is e minus 1 plus some error term.
Okay. So that should have been known from the literature. Right?
Yeah, that is known. Yes.
Yes. Okay.
There is some derangement kind of problem.
Yes.
Or no.
Sort of. Not exactly. No. Derangement would be, I think, you get 1 over e.
Yeah.
1 over e kind of thing.
I was wondering if it was related. Anyway.
So, and what do you mean by error term? Sorry for asking some maybe very naive question. That is e minus plus something that goes to 0 as n goes to infinity. Is that what you mean?
Yeah, that is what I mean. So it's if I'm not wrong, this is e minus 1 plus big O of 1 over n factorial. If I'm not wrong, but yeah, I think the exact expectation is 1 plus 1 over 2 plus 1 over 3 factorial, so on, plus 1 over n factorial. That's the exact quantity, I think, if you do this computation correctly. But again, I'll have to check that. Okay, so all right, so I'll now go ahead. So we are interested in computing this expectation L1 Mn of pi, and So the best known upper bound for this was so this theorem due to Diaconis, Graham, Spiro, and they said that this expectation is upper bounded by m plus big O of m power 3/4 log m. However, they conjectured that this actually should be, I mean, that this expectation should be close to m, actually, m minus small o of m. So we actually show that their conjecture is true. And so now the technical part will begin. So, okay, so we'll make two observations. So first observation, if x is a non-negative integer random variable, then expectation of x is equal to this infinite sum. So this is a standard result from probability. So if you plug in x equal to L1 mn of pi, then you get the sum goes from k to n, because n is the maximum possible value this can take. So probability L1 mn of pi is bigger than or equal to k. Okay, so this is our first observation. Let's look at our second observation, which is if you take the probability L1 mn of pi. So here, okay, so here pi is a multiset permutation from SMN. And if you compute the probability that pi has a one continuously increasing subsequence of length at least k, that is equal to the probability that if you take a tau chosen uniformly at random from SMK, then it has a then its longest continuously increasing subsequence is exactly equal to k. So this so you can just, I mean, you'll have to do a few steps of computation here, but intuitively you can think of it this way. So let's say you begin with a pi. Let's say you begin with a tau from SMK. So you have a multiset permutation from of the number. So the letters are 1 through k, everything repeating m times, such that you have the subsequence 1, 2, 3, so on till k. Now you can insert k plus 1, k plus 2 till n at any position, anywhere in between. So and that will not change your value of that can only increase L1 mn of pi. It will not decrease it. And so that intuitively, this is the idea that you use. And now you have to do a few computations, and you'll get this. So this is our second observation. Now look at this. So we say that tau in SMK has a complete increasing subsequence because it has the subsequence 1, 2, 3, so on till k. If 1, 2, 3, so on till k is a subsequence, and we let hm of k be the number of all multiset permutations which have a complete increasing subsequence. So we obtain that probability of so this right hand side is equal to the number of such permutations divided by the total number of multiset permutations. So now we can we combine the two observations. So first we obtained this. So this was a trivial observation, and then we saw that this from the first observation, and then from the second observation we get that this quantity is actually equal to L1 mk of tau equal to k, and then that is equal to hmk over cardinality of smk. So if you take the limit as n goes to infinity, then you get this expression, this infinite sum. And here I would pause for a while and ask if someone has any questions. All right, so I'll proceed. So now basically, if we want to compute the limit of the limiting expectation as n goes to infinity, it's equivalent to computing this infinite sum. So now this is somewhere within my comfort zone, which
Sorry,
is
I got
yeah.
I got kicked out. What is
Oh,
HM of K? Sorry.
yes. Okay. So did you see were you somewhere on this slide when you got?
Yeah, I got up to tau has complete increasing subsequence.
Right, right. So HM of K is the number of multiset permutations tau, such that tau has a complete increasing subsequence.
Okay, I see, okay.
So the probability that tau has a complete increasing subsequence is equal to the number of such tau divided by the total number of multiset permutations.
Sure. Okay, thanks.
So then now this is from observation 1. You get that this is so L1 Mn of pi, you get this observation, first observation. Then from the second observation, you get this equality of these two things. And then this is equal to HMK over SMK.
Thanks. Yeah.
And when you take the limit n going to infinity, you get so I mean I have changed n k. So I should have probably written k goes from 0 to infinity hm of k over smk, but then I have changed k to n. So in some sense, I mean, now you need only two variables instead of yeah. So I have replaced k with n. So this might be a bit confusing, but just letting you know. And now what we need to do is we need to compute this infinite sum. And okay, this is somewhere from probabilities, this is somewhere within my comfort zone. I can talk about computing HMN and SMN because it's in the realm of enumeration. Okay. So meme here. So what do you do when you have an infinite sum? Try and get a closed form expression for it. Okay. Luckily, we did not have to find an expression for HMN. It was already shown by Horton and Kuhn in 81 that HMN is given by this huge formula. So we will go over this in a while, but then let me just establish the notation here. So here you take I1 till IM. It's a composition of n. That is, it's an ordered partition. So I1 plus I2 plus so on till IM is equal to n, and I1 can be the IJs can be 0. So here the sum over the IJs is equal to n, and L is equal to this quantity, which is summation j ij. This thing over here is the multinomial coefficient, defined as n factorial over I1 factorial, so on till IM factorial. So the usual binomial coefficient would be n I1 comma n minus I1. So that's the usual binomial coefficient. This is the multinomial coefficient. And Horton and Kuhn showed that the number of longest increasing subsequence, number of multiset permutations in SMN that have a complete increasing subsequence is equal to this quantity. Well, this was my reaction when I saw this. But we can actually play around with this. It's not, we'll see, because what we want is not this quantity, but we want HMN over SMN. So let's divide it by SMN. And we in fact know that the cardinality of multiset permutations, that's mn factorial over m factorial power n. So this is something standard that we can see. Okay, so let me bring the m factorial power n to the numerator, and then you can see that let's start simplifying this expression. So mn factorial will cancel out. Okay, now what else can we simplify? There's an n, so minus 1 power L minus n. So I can pull over the minus here. So I'm going to write it as minus m factorial power n and then minus 1 power L. Okay, then I've got this. We're going to continue simplifying. I have switched the two things here. Nothing interesting happening so far. Now something slightly interesting. So observe that L is equal to summation j times ij. So I'm going to write this as product j going from 1 to m minus 1 power j over m minus j factorial I power j. So yeah, so this is again, I haven't said anything much because you can just write ij times. So when you do this product, take this power inside, that will be minus 1 power j times ij, and then you take the product. So you'll get this quantity L, minus 1 power L. That's what you had. And we rewrite this expression like this. Okay. Now let me copy this into a new slide again, and then wonder what would happen if this 1 over L factorial were not there. So imagine that this term wasn't there. Okay. This is, again, this is not very precise. We will get into what that means precisely, but just for now, imagine that this term wasn't there. Then this expression actually becomes something way simpler. You can use the multinomial theorem and write it as summation j going from 1 to m, and then this quantity inside power m, n. And now your infinite, the infinite sum that you had becomes a geometric series, which is way more simpler to handle. All right. So now what we will.
Can you remind
Yeah.
me where the L came from?
So that was some
The sum, right?
L is the sum j times ij.
Oh, okay. Thanks.
Yeah. So that is something which was in this formula that Horton and Kuhn proved. Okay. So and now our infinite sum becomes a geometric series, which is something way more simpler that we can handle. So let's make this, let's formalize this notion. How do we get rid of the L factorial? Okay. So what we do is we begin by defining, so we work over the power series ring over the complex numbers, and phi is this linear map. What it does is, if you give it an ordinary generating function, it will give you an exponential generating function. And this map also has an inverse. So it's an invertible map, which is basically if you start from an exponential generating function, it'll give you an ordinary generating function. That is to say, so it'll look at the power of x and then multiply an I factorial. So if you go in the other direction. So here in this, so phi, what it's doing is you look at this power. So here you have x power I, and then so it just puts an I factorial in the denominator. So that this is how phi, I define phi. All right. Now, so what you can do is, if you have phi of, so this again, so this trivial observation, phi of 1 over 1 minus ax, you can expand this out. So this so by the way, all of these are, we are not concerned about convergence issues as of now. This is at a formal level. So 1 over 1 minus ax is summation I going from 0 to infinity ax power I. You can write that as a power I, x power I, and then you'll get this I factorial in the denominator. And that is equal to e power ax. So a small observation here, and let's continue now. So let's again look at the expression for HMN over SMN that we had. So we had this thing. Remember, if I remove this 1 over L factorial, what you get inside is a power of n. So you get something raised to the power n. Let's again rewrite it like this. So you have minus 1 power L over L factorial and this. So now, anyone has a guess what we do?
We're going to use the phi, of course.
Yeah. So yeah, of course I'm going to use the phi, but how? Okay,
Well,
so
summation jij. So
yeah, I mean, so what I'm going to do is I'm going to replace. Yeah, I mean, the answer, I guess, what I was looking for is I'm going to replace this minus 1 with an x. So I'm going to introduce a variable here, and I'm going to define a sequence of polynomials Pmn of x defined like this, x power L. So Pmn of minus 1 is equal to Hmn over Smn. And so this gives that if you take this infinite sum, then Pmn of -1 is here. I think I have probably made a mistake somewhere. I think okay, so here this indexing starts from 1. I think I may have made a mistake in the previous slides, but I'll check that later in a while. But this is correct. I'm sure about this. So you have Pmn of -1, and then and how can you obtain this? Well, what you can do is you can take capital Pm of x comma y to be the ordinary generating function of the sequence of polynomials in the variable y. So you write summation n going from 0 to infinity Pmn of x times y power n. Then this expectation, this limiting expectation is basically equal to, so you set x equal to -1, y equal to 1, and then you subtract a 1 from it, because you have this extra n equal to 0 thing here. So any questions here? Okay, so let me proceed. And yeah, so now I'm going to, of course, apply phi here. So we've defined Pmn of x to be this sequence of polynomials. We define Qmn of x to be equal to phi inverse of Pmn, because we have the exponential generating function. So if we do phi inverse, we are going to obtain an ordinary generating function. And so this L factorial will go away, and you'll be left with this quantity. And you can simplify this expression and write it as this thing inside raised to an nth power. So this we've seen before, except what we were looking at before, you had x, you had a -1 in place of x. And you can rewrite this. If you notice, this raised to power 1 is basically qm1 of x power n. And so if you take the ordinary generating function of the sequence of polynomials qmn of x, then what you're going to get is 1 over 1 minus y qm1 of x. Okay. Again, I haven't said anything much here. All I've done is I have taken this linear operator phi, and then I've written this out. So I have applied phi inverse to Pmn, and then I have removed the L factorial from the denominator. I've done the computation, and I've obtained this. Now what I'm going to do is I'm going to apply phi and bring the L factorial back into the denominator. And then, but then I'm going to raise this to the power e. We'll see how that exactly happens in a while. Okay, so any questions here? All right, so I'll continue now. Okay, now this, in fact, notice that, so we've defined qmn of x, the polynomial. Sorry?
Get his elbow out of that. So, like you can put your finger through. It happens. You throw yourself. Something happens.
Sorry, is that a question?
Kind of like put a finger between that. Yeah.
Probably not.
Probably not. Okay. So, right. So, okay, here is the observation that we make. So we've noticed, so the way we introduced the polynomials Pmn and Qmn is that Qmn is phi inverse applied to P, or in other words, or you can also say that Pmn is equal to phi of Qmn. But then you can lift this from the polynomials to the generating function, entire generating function itself. So you can actually write this expression, which is
Sorry,
Pm.
I'm confused here. I don't think, is this correct? I mean, you have two formal variables, x and y.
Yeah.
Well,
Well,
you
what you
applied phi in the x variable.
Yes.
But now you are applying phi in the y variable.
No, I'm not. I'm
No,
only applying it to x.
But Pm was capital Pm was a generating function of small pm's in the y variable, right? So
can I annotate here? Let me see if I can, then I can use my pen maybe. Okay. So, okay. Or more formally, what you can define phi. So, oops. Is this visible, by the way?
yes, yes, I can see some D.
I was right.
Yeah, I saw some eraser.
Yeah. Okay. So I was about to write 5, but that turned out to be a D. So I mean, okay. Here you can also define phi from, I should have probably said that. You can define phi from C. You can take two variables, x comma y.
Yes.
So let me write phi sub x to C of x comma y. And so whenever I have phi of summation, a mn, let me not say mn, let me say ij.
No, okay. So, so I was just making sure that you're applying phi in the x variable, right?
Yeah. I'm only applying it to x. Yes.
Maybe it would be just if you just showed us the definition of PM
Yeah.
XY, that would clarify.
So this is summation a I j
X to the
x
I by
power
I.
I y to the j divided by I factorial.
Yes, I agree with that.
Yeah. So I'm only, yeah. So this is the thing that I've done. Okay.
So I'm just concerned that when you write that above equation PM, capital PM equals 5 capital QM, you're not sort of cheating and applying it in the y variable instead.
No, I'm not. Here. Okay. Here, this is phi sub x. But I mean, well, I have deliberately put this y equal to 1 here. Although I mean, yeah, now it's an infinite series in x.
But it's also an infinite series. I mean, you evaluate the series in y, right? Y equal to 1,
Yeah.
right?
Yeah.
Okay,
I mean, you can. So if I write this statement with x comma y, and this statement is correct, but then what is to follow won't be entirely true.
Oh, I see.
Yeah.
Okay, thanks.
Yeah, I mean, if I were to write it, so this is correct, but yeah, I'm only concerned with this. So this is also fine. I mean, this is now a series in x. Here is no y. So I have computed this p and pm and qm at y equal to 1.
But it's no longer formal, I guess.
It is.
In X, yes, but in you substituted in Y. So. I mean, if you take a formal power series, you can't really substitute Y equals 1. But maybe that's okay. I mean,
it is true. I think you are correct, because I mean, I think the coefficients of each power of x are going to be infinite. Is that what's happening?
Yeah, I suppose so. But then again, since you're talking about geometric series and so on, I don't anticipate that you'll run into any very series.
Yeah. So okay. So I mean, this is okay. Maybe I should. Yeah. Okay. Thanks for pointing this out. I guess this is not very formal. What I am saying, what I should have said is PMXY is equal to phi sub x. So I'm taking phi in the variable x, applied to this, and then I'm doing the substitution after that. Yeah, I guess. So let me move forward.
Yeah, sure.
Clear this, and then let's take a look. So if you follow through with this computation, yeah. So if you follow through with this computation, so you had QM So QMXY is going to be this, which is 1 minus QM1 of X. So if you substitute Y equal to 1, and then you apply phi. So yeah, we still do not apply phi, but if you write 1 minus QM1 of X, if you do this computation, you're going to finally arrive at an expression like this, where EM of X is basically the exponential function. So you take the Taylor series of the exponential function and then truncate it at some point. So these are the polynomials which approximate the exponential function. And this is a quantity which has been very well studied. So by starting at a problem of, so we still have to apply phi. We'll get to that. But basically, so we have an expression for this formal power series and y substituted to 1 in terms of this function here. So again, now you'll have to you'll have to believe me, there's a bit of sorcery going on here. I could have showed you the computation, but that's not the point. I mean, yeah, that's basically, you can do it yourself. So any questions here? Because I haven't used the power of phi yet. All right. So now remember that I mentioned a few slides back that phi of 1 over 1 minus ax is equal to e power ax. I'm going to use that here. How? I'm going to split this up. So I'm into partial fractions and then apply phi. So let alpha 1 so on till alpha m be the zeros of this polynomial em of x. And it's easy to see that these zeros are all distinct, simple zeros. Then you can write this out as m factorial times x minus alpha 1 power minus 1 and so on. So by the way, this polynomial is going to be the reciprocal polynomial of not exactly, no, it's not going to be the reciprocal polynomial. Let me just write it out. What is it going to be? All right, so em of x is equal to 1 plus x plus so on till x power m over m factorial. And then this quantity is going to be, so I'm going to multiply an x power m. So I'm going to do 1 over x power m and then what? So this is going to be 1 plus m x so on till m factorial x power m. So the coefficient in the middle is m factorial over j factorial x power j. X power m minus j, sorry. Yeah, hope I haven't messed this up. Summation.
No, but then if you take j equals m, then you get m factorial x power m. So whereas by this formula,
J
oh
equals
no, oh, divided by yeah, so you have to take
divided by j factorial.
This is correct.
this, correct, yeah. Thanks.
Yeah, so this is, yeah, so this is, I think, the reciprocal polynomial multiplied with an m factorial. So this is not exactly the reciprocal polynomial. So I'm taking this polynomial, taking its reciprocal and then multiplying by m factorial. And now, so since alpha, so here you can see that the alpha I inverse, so the alpha inverses are the roots of this polynomial, and you can write it like this. Again, let me clear this and proceed. And so now you can split this into partial fractions. So you can write it as this expression. So it's going to be minus, and so you have to, again, believe me here, do a few computations, and you get this expression. And now when you apply phi, you're going to get minus alpha I inverse times e power alpha I x. And so here, this is the same expression copied from the previous slide. And so this is our first theorem, which is if you take this limiting expectation, its exact value is going to be PM of, so you put a -1 in x. So you are going to get this part, which is summation I going from 1 to m alpha I inverse e power minus alpha I. And you also have to add this -1 part over here, where alpha, so here alpha I are the roots of this polynomial. Okay, so maybe I'll pause here for a while and let you stare at this expression. In the meantime, if someone has any questions, and I have some Mathematica notebooks to show you some interesting properties.
So you're going to tell us what the roots are like?
Yeah, I'm going, okay, so I'm going to, I mean, this is, well, so I'm going to, so after this, I'm going to tell you that a priori, I mean, from this expression, it's not obvious that these numbers are going to be real numbers. So we are going to look at that.
There's a general thing called exponential to ordinary or ordinary to exponential, right? This transform.
Yes, I think it is I think it's general. I mean, I've been told that this was used by still just to compute several integrals, but again, I myself, I am not really sure about. So this has been like this kind of trick has been used by other people quite a lot.
There's an integral form for the exponential to ordinary, I think. Well, we are doing ordinary to exponential.
So I mean,
yeah, that's not the same thing. That's not the same thing that he's doing.
But that may have an inverse, right? That transform.
So, I mean,
no,
so
he's just doing a linear transformation on.
No, but it is the thing which takes the function in. See, you keep the coefficients the same, and you replace an ordinary by an exponential generating function.
So what I am doing is almost an inverse Laplace transform.
Yeah, yes, that's right.
It's similar to an inverse Laplace transform, but I don't want to, I mean, I myself do not know about that well enough, and I did not want, I mean, I wanted to work at a very formal level. And only like, yeah. So that's my comfort zone.
So the principle is that you know what this does on the geometric series. And so you just take your function, you write it as you write its partial fractions expansion, and it's linear.
Yes.
So I
yes.
this is
Yes.
very nice.
Exactly.
Yeah, so simple. Yeah.
So that was the idea here. So now let me show you a few things. Anyone has any questions? All right. So then I'm going to show you my Mathematica notebook. By the way, should I zoom in a bit more, or is this okay? Is the size of the font okay?
It looks fine to me.
Okay. I mean, yeah, I'm not expecting you to maybe look at the specifics of the code, but then okay. All right. So here I have like already written part of it beforehand. So this is these are the polynomials summation x power I over I factorial. Let me define this. So the first polynomial is 1 plus x. The second polynomial is 1 plus x square over 2. Now, so here f of m will give you the roots of the mth polynomial. So let's compute f of 1. So this is -1, which is clearly, you can observe it. So 1 plus x has the root -1. This is clear. Let's compute f of 2. So this is -1 minus I. So this, you can also see that these are the roots of this polynomial. Okay. And now let us compute the expression -1 minus alpha inverse times e power minus alpha. So this is the expression, exact expression of the limiting expectation that we get. So I've defined it. Let's look at what happens to g of 1. Then you get that this is equal to e minus 1. So this is what we were initially discussing. I think someone had asked what happens when m is equal to 1. So when n tends to infinity, this limiting expectation is e minus 1. Okay, let's look at g of 2. So you're going to see it as something complicated here, but then actually, I do not know why Mathematica wasn't able to simplify this. But if I ask Mathematica, what is the difference between this expression and minus 1 plus e times cos of 1 plus sine of 1, then Mathematica is able to tell me that that is actually 0. So this expression is equal to e times cos of 1 plus sine of 1 minus 1. And after g of 2, it becomes too complicated for it to be write it as a simple closed form expression of this form. Okay, so let's compute. Let us compute g of m. I'll increase the precision a little bit. So let us look at this. Let us look at this computation. Okay. So for m equal to 1, you have 1.7 something. So this should, I'm guessing this should be very close to. So here we are looking up to 20 digits after the decimal. So this should be very close to e minus 1, I'm guessing. This should be, this is again, we have an exact expression for this, but then let's look at this. So m equal to 3 is 3.8, 4 is 4.8, 5, 6, so on. So does it, so do you have a guess of what, so you can see that, I mean, so one thing that you can notice is this is approaching m plus 1 as m is increasing. All right. So let me say guess is equal to m plus 1. And let me now look at the difference again between this and guess. Let me increase the precision, 20 digits after decimal. So again, let's take, if again, now if you stare at this for a while, you will see that, so for example, this 49999, so then you'll guess that probably this is 1 over, or if you look at this, then what you will guess is this is m plus 1 minus 1 over m plus 2 actually. So that is from the guess that this 0.05 is 1 over 20. And again, here 0.1 is 1 over 10. So you can make this guess. And let's change our guess to m plus 1 minus 1 over m plus 2. Then this seems to be going to, so this is getting very close to 0. So here at m equal to 20, I have 10 power minus this true, the first 15, sorry, yeah, 13, 14 digits after decimal. So, and so this is what I wanted to show you. And then let me get back here. And I think I'm almost on time. So if you, so we have managed to actually show that this quantity can be approximated as m plus 1 minus 1 over m plus 2. And the difference is an exponential error term. So there's a constant beta such that this is less or equal to big O of e power minus beta times m. All right. And any questions here?
How hard is this about? Is it?
Sorry, what do you mean? As in,
I mean, how difficult is it to get this out? Do you have to use some?
So okay, I mean, well, so to answer that, let me go to the next slide. So Connery and Ghosh in 1988 had proved that this quantity is close to m plus 1. So here, so if you, the difference with our expression is we have alpha I inverse here as a coefficient. So here they don't have this alpha I inverse, they have e power minus alpha I is less or equal to e power minus beta. So this,
they have the same alpha i's, is it?
Yes.
Wow, okay.
So they have the same alpha i's, We do not. So we have this extra alpha I inverse coefficient here. They did not have that. And they proved this. And we basically took their proof and then tweaked it to obtain our proof. And so, I mean, yeah, so this involves a fair bit of calculations. And again, this isn't something that I'm very comfortable with, but I can tell you like the basic idea that you have to do is you take, so you split your set of roots into two different sets. So you have some constant, and then you say that you have some quantity, not a constant. You have some quantity, and then you say that all the roots whose real parts are less than this quantity, you put it in one set. All the roots whose real parts are greater than this quantity, you put it in a large set. So you call these large roots. So you split small the roots with small real parts and large real parts. And then the roots with large real parts, if you expand them out, they are going to give you something which is very close to, they are going to give you the bulk of the thing. And then the rest of it actually goes into the exponential error term. You have to, again, you have to look at some tail bounds. And so when you expand this out for the large roots, only like some finite terms will contribute to this m+1. And then the rest of it, even from the large roots, that just goes into this error term. So this is kind of like the idea, but yeah, it's again quite technical to go into it. So this is, and so our result is, so let's go back. So we have shown that our limiting expectation is m+1 minus 1 over m+2. And if you remember from one of the previous slides, we had this other strategy. My laptop is about to die in a while. Okay, we had this other strategy where you had, you keep guessing 1 till you have guessed 1 m times. Then you keep guessing 2 till you have guessed 2 m times, and so on. In that strategy, so we mentioned that the score was expected score was m+1 minus 1 over m+1. So this performs slightly better. So this is m+1 minus 1 over m+2. So this is our main result in our paper. And we also have another result. So here we have computed the expectation of the, so we've taken, if you remember, again, let me recall. So Li mn of pi, it's the length of a sequence that begins at I. So we have, so the previous result was for L1 mn of pi, but we have computed this as well. So if you look at the expectation of L mn of pi, which is you take the maximum over all continuously increasing subsequence, that is max over all I, then we see that this is equal to gamma inverse of n plus theta of this term here. By the way, am I still, yeah, I have already gone over time, I think, but can I like take maybe 2 more minutes?
Fine, yeah.
Okay, yeah. So here expectation of, so what do I mean by gamma inverse of n? So what I mean by this is, well, somebody can correct me. I think I'll mess up here. But what I mean is you take, if I remember, you take a t minus 1 factorial, you take the largest t such that, so you take the t such that t minus 1 factorial is between this t factorial. So that's the floor of gamma inverse of n is equal to t. So you look at the number whose factorial is very close to n. And so that is going to be, so this is, so you can see that this expectation here is, so again, here we assume n is large, much larger than m and so on. So this is our second result. And so this, So this is kind of like so here the argument, so we had to show an upper bound and a lower bound. So for the upper bound, it followed from Markov's inequality. So something which is standard in probabilistic method. So it's called first moment method. Again, this is not something which I am very familiar with. I'm pretty sure there are a lot of people in this audience who might know more than me. And for the lower bound, we have used some techniques from coding theory. And this is one more thing which I should mention here is if you look at this quantity, you see that, I mean, so our expected score is m+1 minus 1 over m+2. So a priori n could be much larger than m, but our score is, I mean, it does not really depend on n. So the number of suits that you have could be much smaller than the total number of cards that you have. However, this expectation is telling you that the expected score would be around this quantity. And so let me tell you so we have a few conjectures. So in this work, we have computed the expectation of L1, but then what about the higher moments? So this is what we conjecture. If mu is the expectation of L1 and sigma is the standard deviation, then if you take this standardized random variable, which is L1 mn minus mu over sigma for large enough n, this has the same moments as the standard normal distribution. So this
I mean, doesn't
is,
that mean that it converges weakly to the standard normal?
I think so. Again, I don't remember my probability very well. I think that is what it means.
It's a method of moments, yeah.
So yeah, but I mean,
No, so this somehow seems like it may come from some sort of I don't know, it looks like a central limit theorem kind of thing, right? I mean,
yeah, sort of.
but there are no IID random variables which form this thing. So I wonder if there is a model for this L1 MN.
That's interesting. Yeah.
For large.
I mean, I would, if I were to do this, I would look at just compute it and look at for it very formally and till the very end, and then
No, what I'm
make
saying is in the
approximations.
limit as n goes to infinity, can you find some other process which gives this probability?
This quantity.
Yeah, this probability distribution. This random variable.
As so okay.
The
Yeah, I
limited
haven't.
construct something which describes the limited process.
Right. So you mean
As a
you add up IID random variables and then
or maybe not, maybe or maybe not, but at least a probability a process which gives rise to the random variable L1M infinity.
Right.
You're saying the limit exists or something, right? Of L1Mn as n goes to infinity.
Yeah. So I mean, well, I mean, I'm not sure if this would be a model, but you can like consider the infinite word where you are allowed to repeat everything, every letter at most m times.
Yeah, but would that give the right thing? Yeah.
I mean, yeah. So I mean, intuitively, I think that would give. But again, I mean, how would you generate such a thing? I'm not really sure. Intuitively, that seems to be the case, right? But then, how would, I mean, to make sure that it's like generated uniformly, like L1, so pi is generated uniformly from so picked
There's
uniformly
no
at random from
uniform
S and
distribution on infinite sets. So.
right. So this is our first conjecture. We also have expectations for the this quantity. So this is our second. So another one of our conjectures, which is this is equal to m power r plus this term here. And we have managed to prove it till, like, we've managed to show this m power r plus o of big O of m power r minus 1, but we haven't managed to go till here.
The art moment.
Yeah, the art moment. We haven't managed to get this. So a starting point for proving this would be to show that. So yeah, so we want the same moments for this, but then we want, instead of computing the moment of this, let's compute the moment of L1 moments of L1 Mn of pi. Now, of course, one can ask that we are very restrictive in our increasing subsequences, as in we are considering subsequences of the form 1, 2, 3, and so on, or I plus 1, I plus 2, and so on. However, you can consider generic longest increasing subsequences, which are not necessarily, so as in I1 less than I2 less than so on, where I1, I2, and so on need not be consecutive. And this, let's denote it by L tilde Mn of pi. Then, so for m equals 1, it's known that that this expectation is twice of square root of n, and then one can read about it in this book. And it's a difficult problem, and it involves techniques from representation theory. So I do not know anything more to say about it, but then one can consider what happens here when m is greater than 1. So with this, I have, can I show one more thing before
Sure.
ending my talk? Okay. So now let me go back to these polynomials, and let me show you a cool result. So again, these are the Taylor. So you take the Taylor expansion of the exponential function, you truncate it. These are the polynomials that we have. And then if you plot out their roots, they seem to be approaching a curve. So this is, if you take the 50th polynomial, it looks like this. If you take the 100th, you see that it's and then it keeps going, getting denser here, and then it's sparser towards this end. So so this was something which was observed in sometime in the 1920s or 30s by Jagos, and who showed that, so it approaches this curve that we call it's called Jagos curve. And in fact, if you look at the scale here, so here you see that the scale is getting larger. However, what you can do is you can you can normalize this. So you can do complex plot f of 50 divided by 50. Oops, complex list plot. And let me do the 100th thing as well. So if you normalize this, then you'll see that it's actually in the same scale. So what Jagos says is that if you take the roots and then normalize them, so you take the roots alpha I, divide them by n, m here, and then you take and then you plot them, and then whatever you obtain, you take as m goes to infinity, you're going to approach this curve. And so this is one cool fact which I wanted to mention. So actually there's very interesting, so this is something which
I'm
has
just
been
curious, what happens to the curve as you go further to the right?
so it's going to meet here at,
it's going to meet somewhere. Okay, at
yes,
1.
it's going to meet somewhere, I think at 1. So I think that, yeah, so
And is it singular there or is it egg shaped?
it's singular. So yeah, so this is so the roots of these polynomials have very interesting geometry, and this is something which has been studied by several people. And so you can actually, I mean, so when we were computing that expression, we are actually very dependent on this sort of inherent geometry that's there in how these roots are distributed on the complex plane. So maybe this is, yeah, I mean, there is already quite a lot of literature on it, but maybe somebody might be interested and can look up more about this. I do not know much more than this interesting fact here. But with that, I will end by saying that. So let me just conclude by saying that the results that we have obtained. So we've had an epic handshake between techniques from analysis, probability. We've used a fair bit of generating functions and also some computer run experiments. And we've used these to get an exact expression for our limiting expectation, as well as then we've used and then we've obtained useful approximations, because the exact expressions aren't really that useful for us. It's the approximation which is more useful, because it's going to say that it's close to m+1. So with that, I would like to conclude, and thank you.
Well, yeah, thank you. Let's give Vishal a big hand. It's very nice talk. Yes. So, are there any questions? Any more questions? You can just unmute and ask your question. Okay, so I guess surprisingly there are no questions at this point. I thought there would be quite a few. It's very interesting. I mean, yeah, thank you. A lot of I suppose things to be further explored here as well.
So maybe I could make one interesting. I mean, yeah, I can provide one reference, which is, so there will be an article in the American Math Monthly probably sometime soon by Diaconis, Graham, and Spiro. Let me write that in the chat, and that might be something which people can. So there's a lot of history behind this game, and that's something which people might be interested in looking at. It's not out there, but then the article is there on the archive. So I've put it in the chat, so somebody interested can take a look at this. Maybe I can stop sharing.
Yes. So actually, can I? So there's the longest increasing sequence in a word. So you're looking at sequences that start with 1, but one could just look at the longest increasing subsequence.
Yeah.
And that's the first the length of the first row of the shape that you get when you apply the Robinson-Chenstedt correspondence to.
Right.
But here it looks like you don't encounter that kind of combinatorics at all, right? I mean,
no,
because you fix the least element to be 1.
Yeah, I mean, not just the least element, but it's like a very specific kind. Like it's 1, 2, 3, so on.
Yeah,
It's not
no
like
gap,
1, 4,
no gap.
7.
Yeah, no gap. Yeah, that's right.
So yeah, I mean, it would be interesting to see what would happen
But
when.
that other problem should be already understood, right? If you just look for the longest, it's probably something well understood. Maybe in that book that you showed.
So I'm not sure. I think I mean, if I remember correct, yeah, I think like somebody recently tried doing something with m equal to 2, but I don't think that it is really well understood.
For m equals 1, it's the distribution of the first row of the shape under the RSA correspondence.
Yeah.
So it's related to the Plancherel measure for Sn for the symmetric group.
Yes, but then I think I don't think this has been considered, or even if it is, maybe I'm not aware of it.
Okay.
Yeah, again, I mean, this is mostly like these are mostly territories where I do not walk much.
it also seems like it could be related to SM, Reeth, SN somehow.
What?
No. So those are, where you have M permutations, where you have M colors of each number.
Or suits.
Sorry, Apurva, you said something?
Or suits.
Oh,
Right.
yeah. Isn't that, how's that related to this?
So I guess then you look at the longest increasing subsequence, but you disregard the
Yeah, so here
colors or
you're
the suits.
disregarding the suits entirely. There
Yeah.
you're keeping track of the suits. Yeah.
I think so.
So that actually, since that those form a group, and so I don't. But of course, I guess one doesn't really use any group structure here. Yeah. Hey, maybe I'll stop the YouTube.